So, what is a logistic differential equation? Logistic growth usually appears in problems that describe a physical situation modeling population growth. Think of it as a more practical version of an exponential graph because a population can't be unlimited. That's why the logistic model provides a carrying capacity L, also known as the upper limit. So, when you go to make the graph, there is a horizontal asymptote of y equal L. The graph should be continuous on all intervals. Hence, the domain is from negative to positive infinity, but usually it begins at the initial time 0 because we can't go back in time. And the y value may begin at 0 and end at L. It cannot surpass the upper limit. The general solution is presented as y equals the carrying capacity L over 1 plus BE to the power of negative KT, where B is an arbitrary constant. And with some magical math, we can differentiate to find that dy over dt is ky times 1 minus y over L. Now let's take a closer look at the graphs and behaviors. If we take the limit of ky times 1 minus y over L as y approaches 0, y over L would be really close to 0, leaving the limit to just be k times y times 1. We also know that dy dt of an exponential equation is k times y. So this means that in the beginning, when y is close to 0, the logistic equation would behave similar to an exponential and increase at the same rate. Next, we're going to take a look at the limits of dy dt as y approaches L. In this case, y over L would be really close to L over 0. That leaves us with ky times 0, which means that dy dt equals 0 as y approaches L. So when the population of y gets larger, dy dt decreases until it is equal or close to 0. Continuing with the differential equation, but this time we're gonna distribute ky into 1 minus y over L, which is equal to k times y minus k over L times y squared. Now let's take the second derivative of that. Remember that k and L are both constant, so the second derivative of dy dt is just k times dy dt minus k over L times 2y dy dt. Taking out the common factors, we'll have k dy dt multiplied by 1 minus 2y over L. Since we already know what dy dt equals 2, we can simply replace it within the equation. Distributing k to simplify, the second derivative of the logistic function is k squared times 1 minus y over L times 1 minus 2y over L. If we set d2y over dt squared equals to 0, we find that the function would be 0 at 0, 1 minus y over L, and 1 minus 2y over L equal. So 0, L, and 1.5 L are critical points. If we plug y equals 0 into dy dt, k times 0 would be 0. So dy dt is equal to 0. If we plug L in for y, 1 minus L over L would be 0. So dy dt is also 0. If we plug L in for y, however, when plugging in L over 2 in for y, we would get a positive value of k times L over 4. If dy dt occurs on a closed interval that begins at 0 and ends at L, y equal L over 2 would be a maximum. Therefore, dy dt, or the growth rate, achieve its maximum at 1.5 L, half of the carrying capacity. Now that we've been over this in a theoretical terms, what does this all mean? Imagine that you just learned a really juicy story that for sure will cause the biggest scandal in the school, but nobody has known about it yet. So at the time of zero, you are the initial value of a population of people who just heard about the news. You then decided to tell your two best friends, and even though you specifically asked them not to tell anyone, they still told the story to two more people. And those two people also told their other two friends, and soon enough, the gossip started to spread like wildfire. The population of people who heard the gossip grew exponentially fast, and the rates of people who just learned about it also grew super fast. Now, when half of the school has heard about the story, there are the most people who just heard about the scandal at the exact same time. But now, the gossip also begins to die down. It kind of becomes old news at this point. Seems like everyone has heard about it, it's not that exciting anymore. And eventually, the entire school of however many hundreds of people already knew about it. And the rate of new people who just freshly received the information is simply zero. There's no one else in the school to tell the story to because we had reached the maximum capacity. Hopefully, that will give you a better understanding of the logistic growth before we move on to a practice problem. A population of Pt of bacteria in a petri dish satisfy the logistic differential equation of dp dt equals to 2p times 6 minus p over 6,000, where t is measured in hours. Alright, so far we're just given the main equation. Part A, if p0 equals to 350, what is the limit of pt as it approaches infinity? And what is the limit of pt if p0 is 500? Part B, what is the population size when it's growing the fastest? Let's address part A. The limit of pt as t approaches infinity, that is just a fancy way to say the carrying capacity. Because if you look at the graph, as t grows larger and larger, y will approach the upper limit. So what we need to ask ourselves is, what is a carrying capacity? Easy, right? But the thing is, the equation that we were given in the problem doesn't quite look like the differential equation that we worked with previously. Now you can either do some magical algebra to transform it into something similar to the original equation and then look for what L, or you can simply set it equal to 0, using the knowledge that dp dt equal to 0 as it approaches infinity. P will either be 0 or 48,000, the ending population. Now this is a trick question because they ask you to find the limit of two scenarios with different initial values of population. But no matter how the initial value started, it will end the same because the carrying capacity cannot be changed. So the answer is 48,000. On to the next part. What is the population size when is growing the fastest? We already worked this out before. It will be half of the carrying capacity. So the answer is just half of part A, 24,000. And that's it.